Good evening dear viewers and welcome back to my channel. In this video we are going to discuss about the divergence theorem, also known as the Gauss Divergence Theorem. In the last few videos we have seen how do we surface integrate a scalar or a vector field, and also how can we use them to find out the areas of given surfaces. In this video we will be concerned exclusively with surfaces that are boundaries of finite solids. For example, the surface of a solid sphere, the surface of a solid box, or the surface of a solid cylinder, for example. Such surfaces are said to be closed. A closed surface may or may not be smooth, but most of the surfaces that arise in application are piecewise smooth. That is, they consist of finitely many smooth surfaces joined together at the edges. We will limit our discussions to piecewise smooth surfaces that can be assigned an inward orientation or an outward orientation. Let's get started with the statement of the divergence theorem. The statement goes like this: let G be a solid whose surface S is oriented outward, and if F is a vector field with components F, G and H having continuous first order partial derivatives on some open set which also contains G, and if N is the outward unit normal on the surface S, then the surface integral of F dot N with respect to ds is equal to the triple integral over G divergence of F dV. Please note the integral on the left is surface integral while the integral on the right is triple integral. Before we move forward, let us see how to evaluate the divergence of a vector field F. So suppose say vector field F has components F, G and H, then the divergence of F, it is also denoted as grad dot F, and is evaluated as the partial derivative of F with respect to x plus the partial derivative of G with respect to y plus the partial derivative of H with respect to z. And this follows from here. Since the grad is the partial derivative operator, it has components partial with respect to x, partial with respect to y, partial with respect to z, and F has three components F, G and H. And by means of the dot product, this is the result that we end up with. Now let's move on to a simple numerical. So here we have a question that says that use the divergence theorem to find the surface integral of F, where F is given as zk hat across the surface of the sphere given by x square plus y square plus z square equals to a square. To start with the solution, let us first write down F in all its component forms. So since the I hat and J hat components are missing, F bar can also be expressed as 0, 0, z, and therefore the divergence of F is going to be the partial derivative of the first component, which is 0 with respect to x, the partial derivative of the second component, which is again 0 with respect to x, and the partial derivative of the third component, that is z with respect to z. So this is going to give us 0 plus 1, and that is 1. So thus we have that the divergence of F is going to be number 1. And moving forward, by the divergence theorem we have that the surface integral of F dot n hat is evaluated as the triple integral over G of divergence of F dV. And in this case this happens to be triple integration of 1 dV. And we know that triple integral of 1 gives us the volume of the solid, and in this case our solid is given by the sphere x square plus y square plus z square equals a square, and we know that the volume of a sphere is going to be 4 pi by 3 times the radius cube. In this case the radius is a, so we have got a cube, and thus we can conclude that the surface integral of F over S is going to be 4 pi a cube over 3. Let's try and pick up another problem. So here we have the next problem. It says that using the Gauss divergence theorem for F bar given as yi hat plus xj hat plus zk hat over the cylindrical region x square plus y square equal to 9 from z equal to 0 up to z equal to 3, evaluate the surface integral of F. So first of all, in this problem we are given that f of x, y, z equals y, x, z, And since we are going to take help of the Gauss divergence theorem, we will be very much interested in the divergence of f bar, and that is going to be the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to x, and the partial derivative of the third component with respect to x. Again, in this case, we end up with 0 plus 1, which is equal to 1. And by Gauss divergence theorem, we have that the surface integral of f over s is evaluated as the triple integral of divergence of f bar dv over the solid g. So this becomes triple integral of 1 dv over g. And again, since we have the triple integration of 1, this is going to be nothing but volume of the solid g. In the problem, if we will have a look at G, it is said that G is the cylindrical region given by x square plus y square equals 9, z equals to 0, and z equal to 3. And if we try and have a look at the geometry of this, then it is going to be a cylinder like this. The base circle is placed in the xy plane, which is z equals to 0, and it moves all the way up to z equals to 3. And we can clearly see that the height in this case is equal to 3, and the radius of the base circle is given to us as 3, since we have the circular disc to be x square plus y square equals to 9. And since we know that the volume of the cylinder is nothing but pi times r square times h, substituting the relevant values, we get that this is going to be pi times 3 square times 3, and that is going to be 27 pi. And that is the required surface integral. So in this video, we have taken very elementary problems. In the subsequent videos, we will try and take up a little more challenging problems followed by Stokes' theorem. So make sure that you subscribe to my channel and also press the bell icon to get notified for the upcoming video. Thank you so much for watching till the end, and happy learning.